introduce first invited speaker, Dr. Sriram Rajamani, Microsoft Research. So he is one of participants, well-known project Slam, I guess, and now he will present his new research in new area.
Thank you. Okay. Thank you for inviting me, and good morning to you all. Today, I'm going to speak about the title of my talk is Trusted Cloud. I'm going to talk about various problems about security in cloud and a wide range of design issues, ranging from hardware to operating system to compilers to formal methods to start addressing those problems. So that is the goal of my talk. Before I get to my talk, let me first say why security in the cloud is quite different from how security was when we were having laptops and desktops and on-premise servers. Traditionally, the security, we always thought of security as protecting the perimeter, in the sense that all our information is there inside our servers and our machines, and we don't want bad guys to get inside. So we protect the perimeter and keep all of the data inside. This is how security has always been. We think about so since this is a small audience, please feel free to talk to me. I'm happy to take questions even in this. So the whole idea was that we use network firewalls, intrusion detection systems, passwords, two-factor authentication, access control, and all of these mechanisms to protect the perimeter, and then you keep all the value inside the perimeter. This is how security has always been. But I think in the past 10 or 15 years, that has changed dramatically. And the way it has changed is that people have realized that the value is actually outside. And you can't run businesses anymore by keeping the data with you. You have to send the data out to other people's devices, other people's cloud, and that is how you build systems. But the value is in the data, and you have to protect the value of the data as the data travels. And that is the biggest change. So the data can be in applications, it can be in services, it can be in the data centers, companies like Microsoft and Amazon and Google. And the value is in the data, no matter where the data is. So how do you think about security in this context? So that is the overarching theme that is going to be in my talk. So this is a survey that I saw in 2013, but I think it remains true even today. And if you ask anybody, what is the thing that keeps you up at night? Any CIO, they're going to say the worry that somebody is going to hack into the machine and breach all my data. This is the number one problem that people face today. So in this talk, I'm going to talk about how to protect value in data as the data travels in the way. First, I'm going to talk about how to protect the data that is being used in applications and services. Then I'm going to talk about how to protect the data that is present in somebody else's data center. Data center of a company that you wouldn't necessarily trust, like AWS or Azure. And then I'll talk very briefly about how to trust in partners to whom you share the data. So this is going to be, so the majority of my talk is going to be these two, and this I will touch on only very briefly. This is how we talk. So the first thing I'm going to talk about is how do you protect the data in apps and services. Right? And I would say that since this is there are a lot of people using formal methods, I myself am a formal methods person. I will talk about the formal methods, but more than the formal method itself, I will tie the methods to the actual problems that are in this space and how the formal methods can actually help in this space. Right? So context setting is quite a bit of what I will do. So to talk about data use in apps and services, think about search engine like Google or Bing or a social network like Facebook. They own our data. They have a lot of our data. In fact, we pay for using those services by giving up our own privacy. That is how we used it. But there is expectation about how these services use our data. For example, how many of you have clicked in something that says legal in any of these services? Can I get a show of that? Whether it's a search engine or how many of you have clicked on, if you click on this button legal, something comes. How many of you have done it? How many of you have even done a click? See, there's like this is true in every pocket like it, right? Let me show you what happens when you click on this. You get a page like this that is typically written by a lawyer. And this one says, this is for Bing, and you can see the same thing either with Google or with Facebook. It says what data we collect. We collect what you search for, the time and date of your search, your location, your IP address. And then we say what we do with your data and what we don't do with your data. In every company, there is usually an ethics team that actually formulates these things and writes them down. So for example, here, this one was a couple of years ago. The Microsoft website said that we store the search terms separately from any account information. Right? And I think it says something like, IP address we don't keep after 6 months. We throw them away after 6 months. Now, an interesting problem is there are people who write these policies, but these services are incredibly complicated. For example, Bing itself is more than 1 million lines of source code with 77,000 jobs that run on a regular basis. How do you know that 5,000 programmers that write a service like this satisfy those policies that these companies advertise, right? I've spent most of my career in verification, and one thing I know is that what we intend the software to do and what the software actually does are usually not the same. And particularly, the gap grows. The bigger the software is, and the more the number of people that are writing it, right? So how do these companies bridge this gap? They do this manually today. At least when we started this project, that is what the state of the art was. Where there's a legal team that crafts these kinds of policies. Actually, can you just hear me without the microphone? Yeah, I think I'll just speak without it, much more free for me. So there's a legal team that crafts these kinds of policies. And then usually there are these people called privacy champions, because at least in the case of Bing, we sort of think about these data use policies as privacy. And you could, in general, you could think about this as data use policy champions. And then there's people that write code, and then there's usually an audit team that verifies compliance. And usually they're just meetings. So essentially what happens is that people read these policies, and then they have brown bag lunches, and then they familiarize those policies with developers. And developers write code reading these policies. And there's an audit team that looks at how the code is developed to actually verify compliance. This is how it works in companies. So as a verification person, right, I always sort of think about, shouldn't we automate this? Where should we come up with a way by which we take these data use policies and convert them to a formal language and automate the compliance using verification? So this is the first thought we had a few years ago. And what we since then did was we started with Bing, but since then we've actually looked at other systems as well, where we designed a policy specification language for VDBs, where data use policies, like the ones that I showed you, can be encoded formally. And then we have built automated systems that actually take the code the developers write and automatically match them and check them for compliance or conformance with respect to those policies, and build an automated checker that flags potential violations. And one of the biggest advantages of this is that, and I would say that the checker that I've built is both sound and incomplete, and you will see why that is the case. But regardless, as long as this checker is accurate, the potential violations that are produced by the checker give a starting point for the audit team to go fix issues. Right? So the rest of the talk, I'll talk about more this language and how this checker works. Now, one of the interesting things about these kinds of frameworks is that we are not talking about access control, which is how most of policies are actually are. Most policies in literature are about access control. This is about use, it's not about access control. This is about what you're allowed to do with the data and what you're not allowed to do with the data. Right? So here's an example. And I'm describing this language using this example. So this is from Bain. So the policy here says that we will not use full IP addresses for advertisement, but we may use it for detecting abuse. But even in those cases, we will not combine it to account information. And the language, you could sort of think about it as propositional logic, but it is, then we add state and temporal logic and type state to it. And I'll introduce that later. But because these policies are typically exceptions within exceptions, so the way these policies are written is actually something is not allowed, except under certain circumstances it is allowed. And within that, under certain circumstances it is not allowed. Or it's the other way. That is how all of these policies are written. So that's why if you look at our language has alternating deny and allow clauses. But the structure of the language is allow or deny, a data type, and for what purpose. And then you can nest allow and deny alternately. And this is the structure of the language. So here, for example, you can now see one for one how this English paragraph maps onto this language. This one says, you deny this data type for this purpose, except you allow it because when the IP address is truncated, the implicit in that is that we will not use full IP address for advertising, but you can use truncated IP addresses for advertising. Now this modifier is actually type state. So IP address is a data type, and when you truncate it, it changes to a new type, which is this. And that has a notion of state and time implicit inside of it. And so inherent implicit in this logic is time and state. And then there's nested. So you can allow this. You also allow it for abuse detection, except even then, you can't combine it with account information. So this is the structure of this language. There's a paper reference I would give which has the formal semantics of this language. Now, we have been able to encode all of the Bing policies in this language. Not only Bing, we have been able to encode all of Google's privacy policies in this language, and also all of Facebook's policies in this language. Encoding policies is only half the problem. The remaining half the problem is actually how do you check that these big data systems actually conform to these policies. And as a part of this project, I actually learned quite a bit about how these search engines are actually built. And it's pretty fascinating how they are built. The way they are built is by using these systems called Mapreduce programming systems, where the data that comes from the internet comes in as tables. And then you write these Mapreduce programs. They can be written in many languages. In Microsoft, we use something called Scope. There's something called Hive, Dremel. All of these things, they take tables as input, do processing, and then write tables as output. So for example, here is a Mapreduce job that takes two data sets, A and B as input, and you could sort of think about it as something that processes each row, and it might do a join, it might do all kinds of things, and produce a new data. And this might handle billions of rows, even though you could sort of think about it sequentially, and the parallelism is actually what enables it to scale. That is how people write these kinds of systems. And the entire search engine or social network is a combination of millions and millions, I would say tens of thousands of such Mapreduce jobs. That is how systems like this are written. Now, one of the primary difficulties that we ran into when we wanted to check whether a system like this satisfies policies is naming. If you look at the policies, right, the policies talked about higher level concepts and types, such as IP address, account information, right, PII. If you look at these tables are named by programmers to be whatever they want. The columns in those tables could be named foo and bar and temp 3 and phone number 5. You could have all of them. So in order to check these conformance with respect to specifications, one of the first things you have to do is that you have to annotate this program with data types that make sense in the context of the programming, in terms of the policy language, right? And that's not a very easy thing to do. I mean, somebody has to go through this entire big data system and annotate which things are hashes, which things are timestamps, which things are IP addresses, and which processes are what. So it's a very difficult thing to do. That's actually a typical bootstrapping problem that you face anytime you do verification at commercial scale. So one of the first things we did was that we modeled this problem as type inference, right? How systems like ML do type inference is that from the operators, you can actually come up with constraints and then propagate those constraints using systems like Hindley-Milner type systems and calculate the types of all the data. Here, what happens is that there are libraries that programmers use to process these data types. For example, there would be some library that processes IP address, or there would be some libraries that process phone numbers or credit card numbers and so on. So we start with those and we annotate the type information inside those libraries, and then we do type inference to propagate this information via the flows that are present in the program, just like ML does it. So this is the first thing we built a type inference for the system so that we can annotate all of the data types present inside this big data system. It so turns out that the type inference alone was not sufficient. We needed some information from programmers. So what we did was that we built a data flow graph, and we picked a few nodes where annotations from the programmer will greatly help the type inference. So we asked programmers to annotate. In the whole of Bing, we were able to get the system bootstrapped with 200 annotations. And so I think this is pretty characteristic. And since then, I've looked at 2 or 3 other systems. What we find is that using a small number of annotations, carefully selected, you can actually get the type inference to bootstrap for large systems. So long story short, once you annotate the data flow graph with type information, then you look at the flows, and then you find violations. For example, IP address should not be used for reporting. So here, you have a flow where the IP address is used for reporting. Now the tool will flag this as an error. And the way to fix this is that the programmer will have to insert a truncation of the IP address that results in a modification of type state of this type to a truncated IP address. And now the flow passes the checker. So this is roughly how the system works. So we have, to summarize, we have a language. We have a type inference that looks at the actual code and recovers type information in terms of data types that are present in the language. And then we just do data flow analysis to find policy violations. The state of the system is that this system is in active use in several big data systems inside Microsoft. And there's a paper that we published in IEEE SNP, Symposium on Security and Privacy, where the formal details of this language and the checker are present, and I invite you to take a look at it. An interesting new development that is happening inside our company is that, how many of you know about this thing called GDPR? How many of you have heard the term GDPR? The tennis is here. So GDPR stands for General Data Protection Regulation. It is a regulation that is being proposed by the European Union, and it will come into effect in May 2018. And it comes up with a set of regulations that anybody who collects data from people that live in Europe and operates on that have to follow those kinds of policies. Now, there's a bunch of people in our company that are trying to use our system and our language to state those policies and check whether the implementations actually satisfy those kinds of policies as well. So that's all I'm going to say about the first topic, which is how to check data use in apps and services. And if anybody has questions, I can take them now, and then I will go to the second topic, which is how do you protect the data that you send off to data centers. So if you have a question on the first topic, I can take it now, or I can just move on. Should I move on? Okay. So the second topic I'll talk about is protecting data in cloud data centers. And this is a slightly different problem because one of the biggest uses of the cloud is that whatever computation you used to do on your premise by buying your own servers, you now move them to the cloud because it is less expensive. It's cheaper, you don't have to buy the hardware, you don't have to have as much operations staff because the cloud is going to manage the services. So it's less expensive. But one of the things that people most worry about is security, because your data is not within your data center, it is in somebody else's data center. How do you think about it? So it is well agreed now that the main defense against data breach in these kinds of systems is to always encrypt your data. And we know how to encrypt data when it is stored. We know how to encrypt when it is in communication. But in cloud computing, one of the things that we have to also think about is actually how you encrypt the data even when you compute on it. Because when you move your database to the cloud, you're not treating the cloud as a big disk. Right? You're also treating a cloud as an intelligent entity where you can actually process queries. You can do computation. And you want the data to be encrypted even when those computations happen. That is the desire. Ideally, what you would want to be able to do is that any cloud provider, say Microsoft, right, would like to say that they don't have access to the keys. In the sense that we collect your data, we do processing on it, but we can't access it ourselves. So if the government subpoenas us, we can give them the data, but we don't have the keys. That is the situation that cloud providers want to be in, right? And this is a powerful security model because you are now able to get the cloud provider themselves out of the trusted computing base, right? You don't have to trust the cloud provider. You trust mathematics, you trust encryption, maybe you trust hardware, but you don't trust the software in the cloud itself. Let me say a little bit more about it and what it actually means and why do I put always within quotes. Let me contrast how TCB stands for trusted computing base. Let me contrast how we think about trust in the pre-cloud era and how we think about cloud in the post-cloud era, right? In the olden days, we always thought about privilege levels, where the hardware is the most privileged, then the hypervisor, then the operating system, and then the application. Those of you who have done x86 programming know that x86 security is in terms of rings or privilege levels. Ring 0 is the privilege, highest privilege where the operating system runs. And all the user mode code runs in ring 3. And the architecture is such that the operating system can actually look into any application, but the application cannot look into the OS data, which means that if some code runs in ring 3 and then it tries to access any memory that belongs to ring 0, you will get a protection violation. The hardware gives you protection violation. What is the consequence of this? The consequence of this is that you have to trust the hardware and the operating system, which is why, be it Windows or Linux, right? When there's a bug in the operating system, you have to patch it. Because if a hacker can exploit a vulnerability that is present in the operating system, they can take control of the entire system. They can look into any application, which is why patching is so important for no matter what operating system you use. Now that dynamic is changing in the cloud. In the cloud, you don't want to trust the operating system because the operating system is not even running in your premise, it's running somewhere else. So the accepted mode of security is so this red dotted rectangle is the trusted computing base. You want a trusted computing base where the OS is completely outside the PC. Maybe you can trust a little bit of the hardware, maybe you can trust a little bit of the hypervisor. And even if you say the app, you don't want to trust the entire app, you want to trust only the portions of the app. That's the trust model that you want to go with. What does this actually mean? What this means is that in all the places where you don't trust the software, you encrypt the data. When you're still going to use the operating system, but when you pass the data to the operating system, data is going to be encrypted. Which means that even though the OS is hacked, the hacker can actually get access to the data, but you won't get access to the keys. Right? So this red dotted rectangle, which is the TCB, this is the only place where the keys are going to be encrypted. Right? So one of the things that is happening as we shift to the cloud is a rethinking of the trusted computing base to exclude the operating system out of the TCB and maybe trust only portions of the hardware. Ideally, you don't even want to trust the hypervisor, right? So what this really means is that the data and keys are accessible and clear in a very small TCB. And the TCB should not be controlled by the cloud provider. So you're clear about what I mean here? So this is how we want to design these systems, because if you can design these systems, the cloud provider can say, I can't even see what your data is, because I don't know. You don't have to trust me. You don't have to trust my employees, because they don't have access to your data, even if they try. So this is the model that people are moving to. So how do you do this? How many of you have heard about Intel SGX? Show of hands again. ARM trust zone. How many of you have heard those kinds of terms? So let me show you what those are. It turns out that a lot of the hardware vendors are now moving in this direction. So Intel Skylake already has something called SGX. SGX stands for Software Guard Extensions, which are new instructions that are present inside the processor that allows you to create user mode code called enclaves, which cannot be looked inside by the operating system. In that sense, it's a non-hierarchical trust. So enclaves are constructs that SGX allows that a user mode code can spin up. So think about it as a process that a user mode code can spin up. And that process is bounds protected against the operating system, which means that the OS wants to look at that, what's inside the enclave, you can't look at it, right? So our approach is that we are going to create an abstraction called enclaves. And Intel is not the only one who's doing it. ARM has something called trust zone. Microsoft's Hyper-V virtualizer can support these kinds of enclaves. And our work is to use these enclaves as primitives to build encrypted cloud services. So that is what I'll talk about as to how to do that. Now, what is interesting is that you could sort of think about the enclave as a bubble that is protected by the hardware. And one, you might now think that what I could do is I could run my entire cloud service inside an enclave. And I think that's, for a lot of reasons, that is not a good idea. One of the reasons why it's not a good idea is that if the size of your trusted computing base increases, and if somebody is able to exploit a vulnerability inside the enclave code, then they can actually inject a Trojan or a worm or something inside the enclave. And the hardware won't even allow you to do monitoring inside the enclave. Right? Because the enclave cannot be inspected, for better security, it's better to keep the code of the enclave really, really small and even formally verified. And I'll show you how to do that. Right? So it's better to keep these enclaves small. And here's the trust model. The threat model is the adversary cannot observe that what is going on inside the enclave. But they can do everything. They can look at all the code that is outside the enclave. They have root, you can actually even think that they have root permission. You know, you could allow them to hack into the OS, and maybe they can put a rootkit, and they have root privileges inside the OS, right? But they can't look inside the enclaves. That's the trust model. Now, there's something called side channels, which is more complicated, and I will talk about side channels a little bit. But what the adversary can do is that they can actually create new enclaves. They could send messages, receive messages, they could cause interrupts, they could switch context. So one of the things I would also ensure is that the system that I'll present, it doesn't guard against denial of service attacks. In this system I'll present, the adversary can still prevent processing from happening by causing denial of service, and I don't know how to prevent it. There are other methods to prevent it, but I won't talk about those, right? But what the adversary cannot do is that he cannot crack open the encryption and look at the data. That they cannot do, right? Everyone clear about what I'm trying to do? And then I'll talk a little bit about side channels towards the end. The alternative to this approach is actually something called homomorphic encryption, where you come up with encryption schemes where you can do processing with the encrypted data itself. But I'm not going to talk about it primarily because this is not at a stage where it is practical today. Right? These schemes are very inefficient today, and a lot of us believe that it will take several, maybe 10, 15 years before they become practical. Right? So how is the world view of the system? The world view of the system is that the service is going to be composed of trusted components and untrusted components. Untrusted components are components you don't even trust. You don't need to think about anything because the data is going to be encrypted in them. The keys are not going to be present in them, so we don't worry about them. The trusted components are going to have these red dotted rectangles, and those are the only things we are going to run inside enclaves. And those are the only places where the keys are going to be present. Right? As a verification person, I really like this picture, because the security of this system now depends on the security of just the enclave code. Right? So it's a smaller surface that I need to verify. But I have to, I have to trust the hardware. I have to trust the fact that the Intel SGX enclaves themselves cannot be compromised. That's an assumption. But if I trust the hardware, then the security of the system depends on the security of only the encrypted data, only the enclaves. And that's the only place where I need to do inspection or verification or formal methods. Right? And in all the other places, the data is just going to be encrypted, so I don't have to worry about its security. Now, one of the first things we started was actually how do you build this system? Right? The untrusted parts, we don't have to change anything. I mean, we just use commodity operating systems and build them the way they are. But it turns out that even creating these enclaves and managing them is very non-trivial. And the first thing we did was to design an API or an abstraction on how to create and manage these enclaves. That's the first thing we started doing. And I'll tell you why that's an important problem. So we designed something called Shell, which is an interaction API for enclaves. And we designed this abstraction for two reasons. Number one, the hardware platforms that are being used to provide for these enclaves are undergoing rapid changes right now. Right? Intel has SGX, ARM has Trust Zone, Qualcomm is coming with a different chip. There are various kinds of hardware that are supporting it. Even operating systems, hypervisors are supporting it. So there are various kinds of hardware vendors that are providing support for them. So when you are actually a cloud service provider and you want to write software, you want to have a layer of isolation so that as this hardware evolves, you don't have to keep changing your code, right? Because you can't build a million line database and have the hardware change under you every revision. That's not a sustainable model to build cloud software. The second reason is that conceptually, you need to, if you want to reason about end-to-end security of these kinds of systems, you have to have a way of thinking about what these enclaves are and reasoning about their security without getting into the details of all of the hardware. Right? Conceptually as well, you need to have a conceptual notion of what an enclave is for you to just reason in your head what the enclave is doing. And that is actually not very easy. It's very difficult, and I'll tell you why it's difficult. So we designed this API to sort of understand what an enclave is. So our API contains 5 distinct surfaces. One for creating and deleting enclaves, one for doing identity attestation. I'll tell you what this is. It's quite important how to communicate with these enclaves, how to persist secrets, and how to ensure freshness. And to give you an idea of why this is important, let me just go through a scenario about how you create an enclave and then walk through what are the security challenges in just creating and running an enclave, right? And that's it. Imagine now I'm sitting outside the cloud. And I have a binary, foo.dll, that I trust. What I want to do is that I want to give that binary to Microsoft Azure. And I want to ask Azure, hey Azure, spin up this binary inside an enclave, inside your data center. And I don't trust the operating system. Because that's the name of the game. I don't want to trust Azure. Right? So the way I do this, so what is difficult about this? Because you don't trust the operating system, right? As you ship foo.dll, maybe you encrypt it. When the cloud operator spins up the foo.dll, nothing prevents them from injecting a malware along with it. Right? They can just attach, they can actually modify the binary, add their own injection code, and the enclave will contain not just your code, it will contain all the spyware that the cloud provider adds. So do you see what the difficulty is in doing this? Because you want to spin these up without trusting the infrastructure, right? So the way the API avoids this is that it allows you to calculate a cryptographic digest of this foo.dll. Let's call it T. You could do that in your own machine. And then when you ship the DLL, when the create enclave call is invoked and the enclave is spun up, say the first thing that the enclave wants to do is to do a key exchange. Maybe it generates a selected key. And when you want to sign this key with the hardware's private key, the API automatically inserts the digest of the enclave as it is created. Right? So if you inject, if the cloud provider injects malware, then this digest key will be different from the digest key that I did in the security of my home. Right? And so when the message is sent, encrypted by the hardware's private key, on the other end, the user can decrypt the message because they have the public key of the hardware, and then they can check whether the digest D is the same as the digest D that I started with. And that is not the same, they can just stop processing. Right? Of course, I don't know how to prevent denial of service. I mean, the cloud provider can always inject and then this check will fail and I don't know how to make progress, right? But I can always detect. And if malware has been injected, I can detect it and at least stop processing, right? So this gives you an idea of, so this API service is called attestation. Identity and attestation. Identity and attestation is what allows you to get trust on the enclave that runs inside the cloud. It allows you to get the trust that it is my code running on the trusted enclave that runs within the cloud. Now you might ask actually, okay, you've come up with this API. Can you build interesting systems with it? I mean, the only way to find out is to actually build interesting systems with it. And we have built several systems. We have built a version of Hadoop called confidential Hadoop. It's called VC3, where, how many of you know what Hadoop is? A few people, yeah, a lot more. So basically this is something that takes big data tables and does processing on them and produces tables, converts tables to tables. And our confidential Hadoop, what it does is that it is the same as Hadoop, but both the data and the programs themselves, which is the map and reduce code that you write, are encrypted, right? And unlike regular Hadoop, where the cloud operator looks at what's going on, in this system, the data is encrypted, even the code is encrypted. So how the way the system works is that the data is encrypted, and in reality, there's a huge distributed system where mappers and reducers will run, and just the mapper code and the reducer code are going to run inside the enclaves, right? The whole Hadoop scheduler, the whole Hadoop system runs outside the enclave. All of the data shuffling, all of the resource management and everything runs outside the enclaves. Which means that, in Hadoop, right, in traditional Hadoop, in order to hack the system, you can just hack the JVM runtime. Or you can hack any part of the OS and then you will be home free, you can get anything. But in our system, in order to hack the system, you have to hack exactly the mappers of the reducers, which are only hundreds of lines of code. And if you cannot hack them, then you cannot hack the system. I mean, you can hack the OS, but you will get encrypted data. That is all that you will get. Right? So we have built the system. We also built a confidential machine learning system where we run the machine learning algorithms inside enclaves. And the operating system is outside. I mean, just the algorithms themselves, which would be SVMs or neural networks, they run inside the enclave. We built such a system. Another thing that we built is actually a variant where we call it as multi-party machine learning, where we have multiple parties, which could be hospitals, insurance companies, and they pool their data together to do machine learning. And because we can control what runs inside the enclaves, we can attest to it. We have built a system where me as a data provider can actually say, I can give this data, but only under the assurance that I control what you do with it, which means that I want to control what code you run on it. And if I don't like the code you run on it, I just won't give you my keys. I can build such a system, right? And we've built such a system as well. Another system that we've built is a key manager, where so there are these things called key vaults, which are presented in these cloud services, and these key vaults are special kinds of hardware called HSM. How many of you have heard about HSM? HSM stands for Hardware Security Module. Companies like Thales that are present in the UK make those things, right? The way they provide security is by physical isolation. You pay more money, and then you get a hardware security module that is dedicated to yourself. And because there is no sharing, you get security, right? So using those physical hardware security modules, how can you bootstrap security so that the keys are secured throughout the system? And I could, one-on-one, I could give you more details about how to build the system. We have built this system as well. So all of these we built using the simple shell abstraction that I showed you. And we've been building these systems for over 3 years now. Now, the final part of my talk, I'll come to formal methods, and I'll talk about verification, and why verification can play an important role in these systems, right? Then we go back to what the worldview is. The worldview is you have untrusted code and trusted code. And the security of the system just depends on the security of the on-claim code, because that's the only place where the data is present and clean. So how do you ensure the security of this code? Well, one of the things you can do is you just read, as long as this code is small, you can release all the enclave code to the users. You can make it all open source and have people inspect them. That's one way, right? But you can also perform automated verification of confidentiality which is what I will talk about. So how do you do that? Here's an example of an enclave code. This enclave is a reducer in the Mapreduce system that we have built, right? So what does a reducer do? A reducer gets data from multiple sources. It does some aggregate computation on them. Maybe it computes, some function of the data and produces an output. That is typically what a reducer does, right? And all of the enclaves in the system, how do they look? I mean, they get encrypted data. So the data is encrypted. The system first decrypts the data, and then it does some computation, re-encrypts the data and sends it out. This is how you write these pieces of code, right? But what can go wrong in this? I mean, several things can go wrong, right? So for example, this code can just leak the key. If it leaks the key, right, then game is over because the bad guy now has access to the key. You could have a buffer overrun or some other kind of vulnerability inside this code, which means that the hacker can now inject their own malware inside this code, and then the game is over. Another thing that can happen is that the code can carelessly written where data is sent out of the enclave without doing encryption. These are all the problems that can happen inside this code, right? So in CCS 2015, we came up with a verifier that does a bunch of checks on the enclave code and ensures confidentiality, right? So this system was the first system that we built, which uses the SGX enclave instructions and does a bunch of checks to ensure that the code inside the enclave satisfies confidentiality, which means that it takes encrypted data, decrypts, does processing, re-encrypts and sends it out. It doesn't leak any secrets because all of the information that goes out of the enclave is encrypted, right? And to do this, we do a lot of things like taint tracking. For example, we have a type for the key, and we actually chase the key we follow the key as it moves along. We actually keep a bit statically on every piece of data, saying whether the data is encrypted or decrypted. And we do a flow analysis to ensure that the only information that escapes from the enclave is actually encrypted. We do all these checks. And it turns out that this first system was not very scalable. So we built a second system where we decomposed the enclave code into two parts, the user part and the library part. And the first library we built had very bare bones functionality. It consists of memory management, and it consisted of two channels. Two APIs for a channel, send and receive. And implicitly, send always encrypts before sending it out. And receive atomically decrypts and gives the message back. So as a result, right, the code that I just showed you, if you look at this system using the API, when you do a receive, there are no keys in this code. Because the receive implicitly decrypts and gets you the values. And then you can do the computation, and then you do a send. And send implicitly encrypts before you send out. And in this system, the entire address space can be considered as a secret, of the enclave can be considered as a secret. And the only way for the enclave to communicate with the external world is using send, right? But because this is unmanaged code, this is something that you have to verify. You have to verify that the enclave doesn't just write into memory that doesn't even belong to it. And that's the verification we have to do. And we built such a verifier. We gave a condition called information release confinement, which can be more scalably verified. We call it IRC, and we proved a theorem that IRC guarantees what is called confidentiality. And confidentiality is a term that is formally defined in the security community. The way you sort of think about it's a hyperproperty. They call it hyperproperty, where the way you define confidentiality is that if you have two traces, which are sequences of states, and if the traces differ only in the secrets, then as far as the observations that are available to the adversary, the adversary cannot distinguish between them. That is how we define confidentiality. And so we do a theorem that says actually that for these, you could actually check this. And in PLDI 2016, we have built a system where we take user application, instrument using a compiler, and we build a verifier that takes the compiler out of the custom computing base, recovers the structure for the binary, and then verifies that confidentiality is indeed satisfied. And you can read more about this in this paper, right? So what this allows you to do is that it allows you to now verify at the binary level that the enclaves themselves don't leak information. And if you think about it, right, This is actually very scalable, and it's possible because we are not reasoning about the functionality of the enclave. The enclave might be doing whatever computation. All that we are checking is that we are checking that it doesn't leak any information without doing encryption, which is why such scalability is indeed possible. And there is empirical results that I won't go through. The final thing I'll talk about is side channels. And side channels is an important problem, and it is something that we have started to address right now. The enclaves provide a really good abstraction, and so far what I talked about talks about explicit information flow, right? It actually ensures that whatever information you send out is encrypted, right? But it turns out that there is a lot of side channels by which adversaries can learn what is going on inside enclaves. For example, it turns out that the operating system manages the paging. And you have to use, somebody has to manage the paging, and in SGX, the OS manages the paging. So if there's a page fault, the OS would know what is the address of the page which gave you the page fault. The OS has to know that. And that leaks information. And there's a very interesting paper that came in 2017 where just using the page information, I mean, when the granularity is at the level of pages, not individual locations. And the OS won't know what the location that you tried to access is, but the OS would know which page you tried to access. And using just the page information, they can actually use machine learning and infer the values of the secrets that is inside the enclave. So one of the questions we asked is actually, can we plug the side channel using a compiler and verifier? And we have built a compiler which ensures what is called page access obliviousness. We call it PAO. What does it mean? What this means is that because the OS can observe page faults, we want to make sure that the sequence of pages accessed by the program are independent of secrets. And if you could do that, even if the OS knows what pages you're accessing, it's not going to learn anything, right? So how do we do that? And I'll quickly tell you how we have managed to do this. So we first use a type system to ensure that the number of iterations of loops are independent of secrets. For example, this is a decision tree, and here there is a loop that is running on where the number of iterations of the loop depends on the secret. So we force you to write those loops to fixed iteration loops where you have the number of iterations the loop executes is independent of the secret. That's the type system will ensure force you to do that. And once you do that, right, the other thing that we do is the compiler will now generate code in such a way that no matter what code path you take, the sequence of pages that you access are indeed the same. That's what the compiler will ensure. And the way they will do it is that it lays out the code and data pages and inserts dummy accesses to ensure that the sequence of pages in every code path are identical. Right? And it introduces an overhead, and it turns out that the overhead that is introduced can be optimized using MCMC. And I won't go into details of that. And then you can use a verifier to verify that. Right? And we have a recent paper which is going to come up in FSC 2017. It's going to be published in September, where we have looked at several machine learning algorithms like K-means, decision trees, SVMs, and we measure the overhead of protecting against this page fault side channel. Right? So to summarize, so here is a bunch of references. The first one, which is published in 2015, is how to build systems using this kind of API. All these three are verification papers. This is the first verifier we built. This is the most scalable verifier we built, and this is the one that protects against the side channels. That's going to appear in FSC next year, right? The final thing I will say, only very briefly, is sometimes you have to give your data to others, and then you have to figure out what they do with it. And the well-accepted way to do this is using ledgers, where the reason why we trust a bank, right? And I put money in a bank. The bank is not going to tell me tomorrow that, oh, you never came yesterday and gave me money. The reason why that happens is that there's ledgers, and there's processes that make sure that the ledgers cannot be tampered, right? In the sense that when you go, you deposit money, there is going to be an entry in the ledger that the teller is going to make. And nobody is going to be able to void that entry because there's enough processes in a bank that prevent you from doing that, right? So when you share data with partners, right, you need similar ledgers. That's what Bitcoins, blockchains, and so on allow you to do. And we are working on cloud-based ledgers, but this is at early stages, so I won't talk about it right now. So to summarize, right, I think the main takeaway from my talk is that cloud security is very different from traditional security. It's protecting the perimeter and keeping all of the data inside. in the new world, you have to let the data go because that is where the value is. And you have to protect the data as it goes. I talked about 3 things. First one is actually checking policies on data. This is what I demonstrated using the Bing case study, where if you have a service or an app which uses your data, how do you enforce that the data is being used according to the policies that they are supposed to follow? The second one I talked about is actually how do you keep your data safe when you send it to a cloud provider like Azure that you don't even want to trust. And there I talked about how you can actually keep the data always encrypted, even during processing. And what that means is that the processing happens in these bubbles called enclaves. And how do you design an enclave system so that you can actually reason about security end to end? And the third thing that I didn't talk about is actually how do you verify trust in data that you give to other partners, and you do that using ledgers, right? And formal methods have a role to play, but you have to frame the question in the context of the new hardware that is coming up, right? The new trust models that you want, and ask the right questions. And then I think you can actually indeed use formal methods to guarantee end-to-end security of these kinds of systems. So with that, I'll stop, and I'm happy to take any more questions you may have. Yeah.
We have time for several questions.
Yeah.
Maybe my technical question. You need some hardware support, yes? What could we say right now? Do you have enough functionality of hardware support, or you need some?
Yeah. So for example, right? Intel SGX is now released already, right? I have this, I have this Surface Pro that has SGX. So if you have this machine that I have, so it looks like this. This has all this hardware support in it. It contains Skylake, the Skylake processor. If you buy Surfaces, right, they have Skylake, and Skylake has SGX. And in about 1 or 2 years, right, all of the Intel processors in every data center will have this support. ARM is already building something called Trust Zone. We know that Qualcomm is building some. So it's a matter of time before this hardware becomes ubiquitous. Now, in terms of actually whether the hardware support is adequate, today, if you look at the SGX machine that is on my Surface, right, there is limitations on the sizes of the enclaves. The enclaves can be on the order of gigabytes. But if I want terabytes worth of information I need to store, I cannot process them inside the enclave. But that is something that Intel is rapidly fixing. Right? They are adding virtualization support, they are adding paging support, and so on. And the enclaves are going to get bigger with time. So I think the way I would answer the question is the support is there today. The real challenge is that you might ask actually, you have to trust SGX. What if Intel put a backdoor? So those issues are there. And I think they will get sorted out because the hardware landscape is going to get competitive. All the chip vendors are going to provide their own version of these kinds of things, and they're going to compete with each other. And if any one of them gets hacked, the other guy is going to make the money. So there's enough in the ecosystem I see that the hardware support is just going to get better and better. Yeah.
Thank you very much for a very interesting talk. My first question about the first part. And how outsiders of Microsoft or Google can audit that policies actually work as it's advertised?
Yeah, so I think for that actually you need ledgers. What these systems have to do is that they have to be designed in such a way that every operation you do on the data is recorded in a ledger, and that ledger has to be made public. Which, for example, you have to be able to audit every operation that you've made on, right? And you'll have to build systems where so what you have to do is that any time you do operations on the data, those operations have to go through a layer, and there has to be logging and auditing at the level of that layer. That's pretty much the only way to do it. Yeah. And regulators, I think, might enforce. Like that's how it happens in a bank. In a bank, right? Why do we trust a bank? The reason why we trust a bank is that there is enough regulation that you cannot change your account without logging it. That's the only reason, and there's nothing that prevents governments from requiring cloud providers to do the same. And if all your banks move to the cloud, that will happen. Otherwise, you won't be able to trust what's happening there.
And my second question is about performance implications of all these activities for the first part and the second.
Yeah, so interesting question. For the compliance checking that we did, the compliance entirely happens from the logs. We do it more as an audit, and there is no performance implication from that. Now, for the second part, where the data is encrypted and everything happens in the enclaves, there is a performance penalty. For example, the Hadoop system that we built has a 15% performance penalty, right? So the way this works is that any time the data moves from outside the enclave to within an enclave, you have to do an encryption and decryption. That is really the performance cost, right? Now, Intel throws a lot of sync at this problem, where on the data path that goes from outside the enclave to inside the enclave, they do encryption, right? And it is in their interest to make sure that this thing scales. So there is a performance penalty. I think it won't be on the order of 2x. It will be 15%, 30%, something like that. And it will get better and better with time because people will throw silicon at it. Yeah.
Thank you. So I have two questions, and the first one is about the first part when you were talking about data flow, and you said that we need to truncate IP address like on this data flow. So I have this usability question. Do you suggest these fixes, like when you check the rule that like it denies this particular case, but if you change this, it would be allowed?
You could, but currently our system doesn't do these kinds of things, right? Currently our system just shows the flows that violate, and then we let the user figure this out. But I can imagine suggested fixes, right? So in another system I built, Tom Ball and I built a system called SLAM, which actually finds errors in device drivers. There also, we first built the system so that it only finds errors. And over a period of time, we were actually also able to provide suggestions for fixes. And I can imagine that we could do the same for these kinds of systems as well. So the answer is we could do it, we don't do it today, but I can imagine us doing that in the future.
And the second question is about the part with stain analysis. So as far as I understand, for C++ languages, it's a pretty tough beast because you need a very good memory model, and how full is your team?
Yeah, so this one actually, we can do it properly. And the reason why we can do it properly is because if you look at our verifier, we actually control the compiler. Because we control the compiler, what we do is that we generate enough instrumentation in the binary so that we have a bulletproof memory model at the level of regions that we can reverse engineer. So because we control the compiler, we have a completely sound system. But the only difficulty with the system is that if you don't use our compiler, you just try to verify any arbitrary binary, the verifier is not smart enough to detect. So it might actually give you a lot of false positives where, you can actually, your code might be safe, but my verifier may not be able to prove it unless you use my compiler. So we rely on a lot of compiler support in order to verify it. But our memory model is bulletproof. We could probably prove it with HOL or something like that. Yeah.
So it seems to finish. If you have any questions, we have time during coffee break. So thank you again.
Thank you.